So the key points from my presentation are that the USGS 3D seismic velocity model, which I refer to as SFCBM, is comprised of a 3D geologic model and rules assigning elastic properties to all the geologic units within that model. It leverages a wide variety of geologic, geophysical, and seismological information, and has been used in ground motion simulations and in the recent updates of the USGS National Seismic Model. I also highlight the storage scheme that we are currently using. It's flexible, efficient, self-describing storage scheme for any 3D gridded Earth models. They are not limited to a specific geographic coordinate system or a specific region or even the specific data of a seismic velocity model. They are accessed via C, C++, and I'm now adding a Python interface. It's open source software with Mac OS and Linux binary packages. So easily accessible for a very large model. The outline that I'm going to cover are the science drivers, background, and construction of the seismic velocity model and geologic model, the storage scheme, how it's accessed, and I'll briefly touch on future directions. The primary science drivers for the development of the 3D seismic velocity model was input to 3D ground motion simulations. This also includes the fault geometry from the 3D geologic model, and we have 3D elastic properties in the form of density, P wave speed, S wave speed, and attenuation parameters for the P wave and S wave as well. Recently, we've been also drivers for it have been including depth to sedimentary basins in the USGS National Seismic Hazard Model. These are known as Z1.0 and Z2.5. The Z1.0 outlines sort of shallower basins. Some ground motion models use Z1.0. Z2.5 is also very well representative of deeper basins such as the Livermore Basin. We've been using the 3D seismic velocity model for both the San Francisco Bay region and also informing, including basin depths for the Great Valley in the 2023 update of the National Seismic Hazard Model. There have been several 3D seismic velocity models developed for the San Francisco Bay region. One of the first ones was Art Frankel in 1992 following the 1989 Loma Prieta earthquake. It focused on the Santa Clara Valley and looking at the sedimentary basin response, particularly the Cupertino and Evergreen basins. Christian Steidem from Berkeley developed a regional scale model with major geologic units and sedimentary basins in 1999. It is sort of the closest predecessor to the USGS seismic velocity model. There's also been more seismic tomography travel time related work by John Bull in 2000, Cliff Thurber in 2007, Gene Hardebeck also in 2007. Those tomographic models are much coarser in resolution, especially near the surface. They rarely have much resolution in the top kilometers. So they're not well suited for ground motion simulations where we want to include near surface sediments. The USGS 3D San Francisco Bay Regional Seismic Velocity Model was originally developed in 2005 with the primary purpose of providing 3D material properties for recreating ground motion simulations of the 1906 earthquake. It has a detailed model for the San Francisco Bay region, which I'll show just in a couple slides, and it's surrounded by a coarse resolution model. In 2006, R.D. Riders at Lawrence Livermore and A.E. Kim and Doug Drager at UC Berkeley did some initial analysis beyond that, some of the validation we did for our 1906 modeling. They found that the shear wave speed was about 5% too low in the East Bay, but they were sort of difficult to isolate specific regions needing improvement. In 2008, when we shifted over from modeling ruptures on the San Andreas Fault to the Hayward Fault for the 150th anniversary of the 1868 earthquake, we looked at minor updates to correct significant discrepancies. We increased the shear wave speed in the East Bay, and we were looking at comparisons on a larger scale with the Cliff Thurber tomographic model to correct significant discrepancies. So originally published in 2006 with a minor update in 2008. And Evan will discuss in the next presentation updates in 2001 and our current update. This is a map view of the detailed model showing here covering the San Francisco Bay urban region. It's about 300 kilometers by 150 kilometers. And then it's surrounded by a regional scale model that's on the order of 650 kilometers by 350 kilometers. There's only a few geologic units in this coarse resolution regional model, but there's quite a few geologic units, as I'll show in the next slide, for the detailed model. The detailed model, 3D geologic model, was developed by Bob Jackins in 2006. It's constructed from geologic mapping, gravity, seismicity, using Earth vision tools, which are widely used in the oil and gas industry. This includes 23 faults, 29 different lithologic units that break up the model, the volume, into 130 different fault blocks, here all colored by the geologic unit. So you can see cross-section, we have variable dipping moho, we have a variable depth lower crust, and then the upper crust is divided into a bunch of different geologic units with faults shown in red. The water is shown in blue, so we incorporate water, we incorporate topography as well. Here's a cross-section through the Santa Clara Valley, and specifically San Jose, highlighting the Cupertino Basin over here on the west side, the Evergreen Basin over here on the east side. You can see how the faults bring disparate geologic units together, as well as material properties. We create the seismic velocity from the geologic model. So here's our geologic model. We can extract surfaces that create our fault geometry, as well as any of the bounding block surfaces. We combine that with depth information, as well as the lithology as a function, the elastic properties as a function of lithology, to create our seismic velocity model. We generate a grid of points to extract and apply those properties into an external file where a user can provide latitude, longitude, elevation in using different interfaces for various programming languages, and get out the elastic properties, the VP, VS, density, QP, and QS. Here's an example of how we assign elastic properties as a function of depth. These were originally developed by Tom Broker in 2006. This is for the Franciscan in the foothills block as a function of depth. So VP is a trilinear variation as a function of depth with different coefficients for a few different depth ranges. Density is a simple function of VP. VS is a polynomial variation on that VP. QS is a somewhat complicated function of the Schur speed, and then QP is a function of QS. We've had some recent updates, as I mentioned, in 2021, we did a re-release in our new storage scheme that I'll discuss in a few minutes. We also had a significant updates to the East Bay based on ground motion simulations of moderate earthquakes, and we're preparing an update to release in the next few months. In the next few slides, I'll sort of give an overview of some of this new storage scheme. It's based on HDF5, which is a widely used scientific data format. It builds on our previous storage scheme, as well as the IRIS sort of coarse resolution storage scheme for velocity models. And we have API for serial access and binary package for Linux and macOS. In terms of discretize our model, we actually include very fine scale variation near the surface. In the top 500 meters, we have a horizontal resolution of 100 meters, vertical resolution of 25 meters. Down, once we go deeper, we go to a slightly coarser 200-meter horizontal resolution, 50 meters vertical, and then it jumps as we go down to 3.5 kilometers and then below 10 kilometers. At the regional scale, we don't have as much horizontal or vertical resolution, and so we can use a coarser discretization. And I want to highlight that in our new storage scheme, we do a linear interpolation, and so our actual variation is even finer than how we've discretized pointwise in rasterizing the seismic velocity model. This is a map view of the shear wave speed at the surface in our current release. You'll see we have very low velocities around the perimeter of the San Francisco Bay. You can see some of the fault blocks, how they show discontinuity and material properties across that. You can also see more sediments in the valleys in the North Bay, also down in the Santa Clara Valley and around the perimeter of Monterey. And then harder, stiffer materials underneath the mountains and hills in the East Bay. Down at a kilometer, we have a little bit less variation than we did at the surface. Here's the Livermore Basin. You can see the bedrock cropping out in a bunch of areas. Well, we also have some soft sediments offshore in the Pacific, underneath the Pacific Ocean. 1 kilometer, we start to lose our spatial variability just because things at that depth become generally more uniform, and down at 5 kilometers, it's also quite uniform. If we look at a cross-section, this is a cross-section through San Jose, similar to what I showed before in the geologic model. These are the different geologic units, and then now I'm going to just overlay what the seismic velocity model is in terms of the shear wave. And as I slip back and forth, you can see how we translate the different materials, and you can see the sediments near the surface. We have deeper sediments in areas based on the geologic unit. Here's the Great Valley over here to the east, and the Cupertino and Evergreen Basins in the central Santa Clara Valley. Our storage scheme before 2021, we were using something that was developed out of Carnegie Mellon that was based on octrees, where you can subdivide a grid and have finer resolution, and you can have this spatially variable discretization. And so this was attractive back in 2006. We didn't have to develop all of the necessary storage scheme for this, and we just built our own custom C++ Fortran API on top of a Carnegie Mellon library. One of the great things is only a part of the model was loaded into memory at a time. The detailed model was 9 gigabytes. The regional model was 6.5 gigabytes back in 2006. Many computers, if you were trying to access, that was a lot of memory. And so we wanted to be able to load a small portion in at a time. Some of the difficulties with the storage scheme was it ended up with stair-step at the top surface associated with these octrees. The underlying file format was completely opaque to the user, so they had a difficult time understanding it. When the Lawrence Livermore SW4 group started to run use this model on some of their newer supercomputers, they were big endian machines. I think they were Blue Gene at the time. The model was created on little endian machine, and even though the Carnegie Mellon library supposedly understood endian types, it didn't know how to switch back and forth and do the swapping properly. So there was issues related to, and we realized at that point that the Carnegie Mellon library wasn't as portable, and due to the fact that things were opaque, it was very difficult to move forward in that direction. So for the 2021 update, created a new storage scheme. It's a completely self-describing binary format built on HDF5. We can support models with and without topography. It can store models in any georeference coordinate system supported by the Proj projection library. We can have variable horizontal and vertical resolution with depth. The vertical resolution can be independent of the horizontal resolution. And we currently have a serial API with plans for a parallel API for it. And with using HDF5, we can enable seamless compression. So now our detailed model, even though we have essentially the same underlying resolution, its storage size is only 2 gigabytes compared to 7 or 8 before, and our region model is just 1 gigabyte. This is how we handle the storage. So in the physical scheme where we have topography, we have basically a stack of grids that conform to topography, and we have curvilinear grids with variable resolution at depth. Internally, we store it as basically a stack of grids, and we have a linear mapping between the two based on our surface topography, which we have now explicitly incorporated into the model. We use, as I mentioned, the HDF5 storage scheme. Here's just a general layout, simplified layout of information that it includes. It includes a lot of metadata and attached to various data sets, like the one for the topography, and then we have these blocks storing the elastic properties. I'll just highlight a few. We have a description that includes things like the title, an identification, description keywords, a version. We have attribution, so who created it, where they're from, acknowledgements, references, how to cite those models, such as a DOI. We have information about the contents. As I mentioned, this isn't just specific to seismic velocity models. It can store a variety of data. In particular, things like what the Southern California Earthquake Center uses, such as stress models, thermal models, rheology models. So we can store a wide variety of data. So you have the values, the units, auxiliary information, complete georeferencing information, and you can have a local origin. It can be rotated, and you have the dimensions in each direction. And for our API, we have command line tools where you can query for values of the model, just given a text file with things like latitude, longitude, elevation. You can query for the elevation of the top surface. You can extract all of the metadata, dump it out in an easy to view format. We also have high-level interfaces for things like 1D vertical profiles. So if you're wanting to know what your site response is at a particular site, you can just simply extract that information, giving it just a few parameters. For our C++, Python API, it's a library accessing models in serial. We have 98% test coverage because we want to make sure that everything is working properly on a variety of platforms. There are a few limitations, and these mostly deal with the fact that we have discretized information that has sort of abrupt discontinuities, particularly across the water-solid interface. So VP and density are interpolated across the water-solid interface. VS is not defined in water. And so grid cells that span that water, or a point that was within a grid cell that has spans that interface, we are not able to provide a value right now. We're working on how to deal with this interpolation and identifying of these interfaces. Again, also our fault block and zone IDs, those aren't generally useful for the user, but they, if you want to know what geologic unit, those are interpolated across the geologic units, which can cause some problems. We have not yet implemented a public API interface, but the Lawrence Livermore SW4 group has implemented a custom implementation. And so would like to work with them to develop a public implementation that would work for a variety of ground motion simulation codes. I should mention that all the documentation is on geomodelgrids.readthedocs.io. Release information, version 21 is available on the USGS Science Base. Rather than try and hunt down the DOI, either look at our paper that was published in 2022. Also, the easiest way to find it may be to just Google my last name and version 21.1, and that tends to come out on top for these two releases. As I mentioned, the documentation for geomodel grids, it points to the repository where you can download the releases with installation instructions and how to use the binaries. We are not developing this model in a complete vacuum. In 2018, we held a workshop, and in 2020, we published a 5-year science plan for how to improve the model. It's available. We're sort of running at the end of those 5 years, but we've generally followed along those guidelines. Looking farther forward, the Southern California Earthquake Center is now the statewide California Earthquake Center. In recognition that many models exist beyond those produced by SCEC researchers in terms of community models, we are holding a California Communities Models workshop online this coming March. and some of the questions that will be addressed in that workshop are: what are community models exist and where within the state of California? How do we coordinate community efforts? And look for if you're interested in participating in that workshop, look for announcements coming out on the SCIC and the ERSCOPE mailing list. And finally, I may not be able to participate in sort of the end discussions today due to parental duties, but I wanted to highlight the fact that Cosmos has a simulation working group with the objective of developing international standards and guidelines for curating, validating, and disseminating simulated earthquake ground motion data for engineering applications. Many people in this workshop participated in the Cosmos 2022 workshops. The report on those workshops is available on the Cosmos website under projects in the simulation working group. We've also been holding sessions at conferences. There were 3 conferences in 2023 that had various sessions related to simulated ground motion data that Cosmos Simulation Working Group helped formulate those. There'll also be a special session or a session at the 2024 World Conference on Earthquake Engineering this upcoming May. And we are partnering with other groups to engage the community on these topics. There'll be a planned workshop that we're just starting to formulate the plan for in September. That's going to be a joint Cosmos and Geo Inquiry workshop in Potsdam, Germany. I think the PEER-Lawrence Berkeley National Lab Group would be another, possibly do more coordination related to these workshops. And the Cosmos Simulation Working Group is continuing to seek funding for in-depth workshops to actually develop those standards and guidelines that can be broadly applicable across, groups in Europe, the US, New Zealand, Japan, Taiwan, across the world, so they really coordinate and make simulation data as well as available as recorded ground motion data, and perhaps the merging of those even easier on a broader scale and from many different groups. So thank you for your time, and I look forward to our discussion.